Good evening from India. Thank you so very much from connecting from all over the world. Your presence makes everything so special and worthwhile. I'm not just talking to my former students, but there are several new people who have joined. And again, my heartfelt gratitude to Amita and Anuradha for bearing with us with a lot of unusual requests that have been doing with such grace and humor. So a little bit about the summary about what we covered yesterday. Yesterday was mainly centered around tenets of sustainability in ancient settlements. So we first explored how the ancient Sri Lankans invented the concept of hydraulic air conditioning and how they ensured that the Buddha's relics enshrined in the Jetavana Vihar, Ruan Valley Stupa, they could be preserved for posterity in a kind microclimate. And we also studied how they managed their water resources so that cultivation was possible and the dormitories were comfortable. Then we looked at 1,000-year-old Jain settlement in Karnataka. And we were specifically looking at comparisons between modern day structures and ancient structures and what aspects of vernacular idioms can be reiterated in the present day. And today would be, I've called it Showers of Grace, how the monsoons shaped Indian civilization. And again, some other tenets of riparian architecture that are fed by the monsoon rains. So what you see here are recent pictures from Pondicherry, where Amita, Anuradha, and I come from. So what you see is billowing and ominously threatening rain-bearing clouds on the left, and how the built environment with distinctive colors, gray and white to distinguish, these are ashram buildings, how they react and somehow gel with a monsoon kind of setting. Why isn't this moving, Siddharth? The screen has to move. Sorry, the screen seems to be stuck. What's happening? Is the internet?
No.
Yes. Is that the second slide? So before we begin to understand the attributes of those rain-bearing clouds and how the monsoon falls, it is absolutely crucial that we understand where they are positioned on planet Earth. So I'll be using my pointer. So those rain-bearing clouds over Pondicherry are hugging the lowest layer. They're actually on the Earth's surface. Here you can see the wavy structures corresponding to the sea that you saw, and they are in the troposphere. And the Mount Everest is almost touching this lowest layer of the atmosphere, the troposphere, where it's very dramatic in the troposphere. You have thunder and lightning and cloud formations, cyclones and gusty winds and all the rest of it. But just above the troposphere, and you can see a cloud and then with a flattened base, and above the troposphere, you have the stratosphere. And the word stratification implies an attribute of layering. And within that sits the ozone layer. And before I proceed further, I would like to point to something very positive that has happened over the ozone layer. We have been hearing about the climate summit, the recently concluded one at Glasgow, where the world leaders debated and all of Greta Thunberg's activism and many governments' reluctance not to act on ameliorating the current climate situation, we tend to believe that all is doom and gloom and we cannot reverse climate change easily. That's going to be really, really difficult. But the success story is, again, this was mediated by the Kyoto Protocol initially. There was another protocol in 1987. It's called the Montreal Protocol, where again, all the heads of the governments and citizens, they acted together. And the success story is with the intervention of the Montreal Protocol, the ozone layer is almost healed. So human intervention did something quite positive, and in another 10 years, we wouldn't have an ozone layer. That was because refrigerants are differently manufactured, chlorofluorocarbons are no longer used, and even refrigerators in Pondicherry, I see stickers, CFC free. So the point to take is, above the troposphere, we have a layer which is stratified, and it is quite thin. It hasn't got as much air as in the troposphere. So recently, people are talking about one way of an engineering intervention to combat climate change is to inject particles into the stratosphere so that the injected particles would reflect radiation back to space and cool the atmosphere. So that's one engineering intervention. And apart from the solar farms that everybody knows, tapping in solar energy, but there have been debates in the public media, and certainly Amitabh Ghosh have been reading up since last night. I mean, many people feel that is not enough. I mean, unless a discourse permeates entirely within every strata of society, in the realms of literature, theater, public consciousness has to change. This is a much more difficult problem to solve, but not insoluble. So that is point number 2. And now, so for the public consciousness to change, and here we are talking about poetic and literary synergy, one mechanism of awareness done through poetry and literature to kind of consummately alert society at large. So I'll quote Sri Aurobindo from the book of the Traveler of the Worlds. Above, in a high, breathless stratosphere, overshadowing the dwarfish trinity, lived aspirants to a limitless beyond. Now, this was written at the turn of the 20th century. And I'm very surprised that he uses the word breathless, for indeed the stratosphere is quite thin in air. I'm told by Dr. Nirodbaran, mentors to many of us, that Sri Aurobindo would read the Hindu every day. And that was when quantum mechanics was already developed, and Einstein's theories. So he was quite engaged. I'm sure there must have been references about the layers of the atmosphere. And this is high poetry written in blank verse. He uses the phrase breathless stratosphere. So, and then he also writes and moves in a pure, free spiritual realm, as in the rare breath of a stratosphere. There's a reiteration about the rarefied stratosphere that is so crucial about the conservation of life on Earth. So still going back to the diagram, if you turn your attention to the red curve, so there's a red line with a constant gradient, which is showing that the temperature is constantly decreasing with height in this lowest layer. And that's the farthest limit where aircrafts can fly. Aircrafts can't fly above that layer. And the temperature there is -60 to -90, freezing cold, and you have frozen clouds. And then you have outer space much higher up. So what is important to understand is the monsoon activity is happening much lower down. So I think I can proceed further. So the high drama of the monsoons is captured certainly in Sri Aurobindo's poetry. Rain tide burst in upon torn wings of heat, startled with lightning's air's unquiet drowse, lashed with life-craving streams the torpid soil, overcast with flare and sound and storm-winged dark, the star-defended doors of heaven's deep sleep, or from the gold eye of a paramour, covered with packed cloud veils the earth's brown face. Mark the use of words. Rain tides is saying there's gushing rain that is borne upon by torn wings, is referring to swift moving clouds and lightning. And then he's used the word life-giving streams. Without the monsoons, subcontinental civilization would have perished. And he uses the word torpid soil. And let's listen to how the mother reads a bit of the line. Even Sri Aurobindo's collaborator was very sensitive to the environment, and she read out loudly from the Savitri.
Rain tide bursting upon torn wings of heat, startled with lightning as unquiet doors, left with life-giving streams.
So she's trying to read those very lines, and Sri Aurobindo has quite tellingly describes what happens when the monsoons have not yet arrived. So we shall see how the monsoons arrive.
Every year, as the summer sun climbs in the sky over the northern hemisphere, one of the world's most dramatic seasonal changes begins.
The onset of the monsoon rains over South Asia and the start of some of the wettest weather on the planet. Although many people associate monsoons with heavy rain, the word actually comes from the Arabic word mawsim, which means season.
Monsoonal climates are defined by a seasonal reversal of wind direction, heralding a change from a dry season to a wet season. More than 60% of the world's population live in regions affected by a monsoon climate. One of the best known is the monsoon that impacts much of South Asia. In parts of India, the seasonal change from dry to wet is so well defined that many areas receive 90% of their yearly rainfall during the summer monsoon. A dramatic seasonal change every year, but powered by a very basic mechanism.
Simply put, land heats up more quickly than water. It's something we often notice on a sunny day, even here in the UK. Dip your fingers in the water, it can feel quite cold. Lay a hand on the ground, heated by the sun, it can be very warm.
And as the sun gets stronger in the skies above India and Pakistan between March and May each year, the heat builds. By the end of May, temperatures can soar to the high 40s Celsius and even the low 50s. Meanwhile, the surrounding seas are much slower to warm up and remain 20 degrees cooler.
Warm air is less dense than cold air, and when the heat rises over the Indian subcontinent, the air also rises. A huge area of low pressure forms, creating a vacuum effect and pulling in much cooler air from the southwest. It's at this point that the dry northeasterly winds from continental Asia are replaced by southwesterly winds, loaded with moisture from the surrounding Indian Ocean. This is a southwest monsoon, the abrupt change from a dry season to a wet season.
So across India we see the monsoon onset across southwestern parts of the country around the turn of the month, May, early June, and then it moves northwestward through the next few weeks and it reaches northwestern parts of the country by around mid-July. But it doesn't progress any further than that because we have the Himalayan mountains in the way. And as a result, what we see is the heaviest rainfall measured in the world across northeastern parts of the country, which is just on the foothills of the Himalayan mountains.
Months of relentless rain falls on Simran during the southwest monsoon as rain-bearing clouds are forced to rise over the Himalayan foothills. Whilst the UK receives on average under a metre of rainfall a year, Simran receives annually almost 12 metres. Although the monsoon rains are essential following the long dry season, flooding can become a big issue for communities throughout South Asia.
As the sun loses strength during September and the land cools following the seasonal rains, another wind reversal occurs.
Now this happens during the Northern Hemisphere autumn, and as the monsoon winds retreat, so begins the next dry season.
So that more or less summarizes how the southwest monsoon forms and then how the northeast monsoon takes over. So, but additionally, I'd like to point out that we tend to believe that the monsoons have existed over the Indian subcontinent forever. Monsoons appeared on the subcontinent only after the Himalayas appeared with continental collision. So why? This was not mentioned in this video. When you have moisture-laden air, it needs a thrust for a very rapid upward ascent. And that is affected when this moisture-laden air dashes against the Himalayan wall and rises up very quickly. The key word is quickly. So in a thermodynamic sense, this quick rising, as you'd seen on the graph earlier, cools the air quite fast. And when that cooling happens, the air cannot stay as vapor any longer. It has to condense into droplets. So the monsoons appeared. Civilization was shaped only after the Himalayas appeared on the face of the planet. So we'll move on. Now, I want you to understand very carefully what is presented in this table on the left. We tend to believe that we have the received precipitation is so much that we have almost an inexhaustible supply of fresh water available to us. The statistics that I'm going to present here from Wallace and Hobbes, that's where the surprise comes from. So the first column is the reservoir of water. We have atmosphere, fresh water, lakes and rivers, underground water, alpine glaciers, Greenland ice sheet, Antarctic ice sheet, oceans, the crust and the mantle. So these are all the sources that one can count on planet Earth. And the next column tells us the mass per unit area in thousands. There's a multiplication of 1,000 per unit area of the surface of the Earth. And the third column is the residence time. How long is this going to reside? So mark that monsoon with all the drama that it unleashes with flooding. The percentage is 0.01%. The residence time of a cloud, it's referring to a monsoon-bearing cloud, it's a few days. And freshwater lakes is much higher, lot more is contained in the freshwater lakes, and underground freshwater is significantly higher. And there is concern that our water tables are depleting. We are sort of sourcing fresh water out far too much than we are putting it back. And that can last up to hundreds of years. Now in Auroville, they are doing projects on to map the extent of underground water in the Aurobindo region and underground tanks. And again, alpine glaciers, the residence time is a few hundred years. The Greenland ice sheet holds a lot of fresh water and lasts for about 10,000 years. The Antarctic ice sheet, even more, 10 times more, 100,000 years. Oceans, it's not fresh water, it's salty water. But the surprise comes in here. The crust and the mantle, which is below underground, has a massive reservoir of H2O water in the form of steam and lasts for over 1 billion years. Now, technology has not developed to such an extent that if a technology were to be developed that we can extricate water vapor and steam from the crust and the mantle and somehow condense it into droplets, only then we would have a perennial supply of water. But the catch is engineering is so far advanced that we cannot drill beyond 200 kilometers. It'll be so hot, all your sensors, all your equipment would melt. So what we see is the received precipitation is minuscule. What is this? Yeah. Received precipitation is absolutely. Listen, there's some background noise in the. It's interrupting my. Yeah. Yes. Received precipitation is absolutely minuscule. And what we saw yesterday, residents of Anuradhapura and Aratipura, thousands of years ago, they had to deal with an insignificant amount of received precipitation, and yet they managed it so well that those cities flourished sustainably for 1,000 years with this limited amount of water, and they were comfortable. So then we look at this picture on the right. This is, so the raging drought that we see, is it because an El Nino event? El Nino is a warming up of the Pacific Ocean waters. Is it because of a failed monsoon, dried bore well? And then the trauma that it unleashes, the Great Famine of 1877, the underestimated official death toll was over 5 million in 1 year. This alludes to the vagaries of the monsoon. Then in 1877, we had an El Nino, which was strongest on record. Now for this year's monsoon, the India Meteorological Department has predicted that El Nino is not going to be very strong. So we are quite lucky. For 3 years in succession, we've had quite a good monsoon. The 1877 was strongest on record. So climate models predict that future El Nino could become worse. Every time there's an El Nino event, the monsoons are suppressed. So that is telling us that, point number one, we have to live with a minuscule amount of received fresh water from the atmosphere. But what we receive, if that is managed very well, we can live comfortably. So now let's see how this situation is poetically described. I'll be only using Sri Aurobindo's poetries for today's lecture. There are lots of other poets who have talked about a little bit of Tagore towards the end. So let's read some of the beautiful lines that he has written. Paced summer with his pomp of violent noons, and stamped his tyranny of torrid light. You can see that. And the blue seal of a great burnished sky. Next through its fiery swoon or clotted knot, rain tide burst in upon torn wings of heat. Startled with lightning air's unquiet drowse, lashed with life-giving streams, the torpid soil. This is what the mother read. Overcast with flare and sound and storm-winged dark, the star-defended doors of heaven's dim sleep, or from the gold eye of a paramour covered with packed cloud veils, the earth's brown face. This is from the book of Birth at Quest. The preceding weeks, what we are going through at the moment is captured very well. We are athirst for the onset of monsoon. Continuing on with trauma of lived experiences, to put things in context, that year, 1877, the population was only of the order of 200 million. This is the globe. And the projected Indian population is going to be 1.64 billion in 2050. Then quite recently, the Northeast monsoon, the BBC video explained how that forms. It's called a retreating monsoon. There was a severe drought over southern India where we currently live, and with a concomitant water scarcity. And in June 2019, there was a 0 day in Chennai. I remember that. Groundwater depletion was almost total and the reservoirs dried up. Water tankers had to be brought in from elsewhere to feed Chennai city. Then in 1877, farmers in Tirunelveli and Tanjavur, the rich farmers were largely unaffected, but the landless laborers in Arcot, we are very close to Arcot and Vellore, they were quite vulnerable. And today what we see is wealthy farmers will do well, but not so wealthy farmers that thrive on a rain-fed farm. This might be the norm. So the summary is received precipitation geographically variable and seasonal temporarily skewed. So now even today's newspaper has reported studies from the Scripps Institute in America saying that these peaking in global mean temperatures is going to be quite a norm this century. And will farming communities need to brace for increased crop failures? Now, I did some geoengineering modeling studies with my colleagues at Leeds. And what we found in this study, if I can share a copy, that small farmers in Tamil Nadu, particularly people who cultivate groundnut, are going to be very adversely affected by climate change. So drought is a killer in India's growth story. So the picture on the left here, 2018, we have a completely full reservoir. And the next year, when monsoon activity was suppressed, it's almost dried out. So the storage of water of the 6 major reservoirs in Tamil Nadu is going to be affected. And statistically, the worst drought years in the last 15 years, 1980, 82, 83. So in the 80s, there were quite a lot of bad years. So this shows what happened in the Mandya district. We studied that yesterday about the Jain settlement. So why there appears the resistance was a rain-fed reservoir that they embellished so artistically to aerate their dormitories. So in that district of Karnataka, from 2015 to 2018, there was deficit monsoon, the negative signs. Sometimes it was 34% deficit from the norm. So that is from one extreme to the other extreme. So in Chennai city experienced a day 0, and a few years later, it was so flooded that airlines had to wait. And my dear student friend Dhruv went out on voluntary work on a boat to rescue people. So he lives in posh T Nagar, but he moved out to many vulnerable areas to rescue people. So one extreme to other, intense precipitation, the Indian's perspective. So we have extreme floods as well. So why is that happening? So this is Chennai, and you see skyscrapers, rapid urbanization to missing links of storm water. So earlier the ground was more pervious. Water could trickle down onto pervious ground, with sort of unplanned urbanization and the concreting, not only is it increasing the urban heat island, making the city centers hotter, but it's not able to soak up the sponging action of the ground is completely switched off. So we'll be focusing on Chennai city, where it's almost comparable to the population of London. So the elevation is not very much, it's quite flat. And what you see in blue are patches of natural reservoirs. And then you can see the coastline of the Bay of Bengal, where you have a lot of moisture being brought in. So bear that in mind. Now, what has rampant urbanization done in these very areas? I'll go over this quite slowly. So the colors in yellow are the built-up areas by the year 2000, a shade darker, 2010, and in red by 2015. So what you can see is what was black originally, you are seeing a sprinkling a lot of reds, indicating high urbanizations quite rapidly. And we will explore what this is doing to the storage of water. So these are certain parts of Chennai city, Enmore and the Pura Lake. And when Chennai logged the wettest November, I think October 2021, Chennai received 200 millimeters. That was a deficit by 22%. Then the next month, a few weeks later, 79% excess rainfall, wettest recorded rainfall, and the city was inundated. Then November 1915, again, it had very high rainfall. So the winter, now Chennai, much of the rainfall is from the retreating monsoon, the northeast monsoon. So these areas, winter monsoon rainfall, we've shown the actual rainfall amounts, the normal amount, and the departure. Over 1,000% departure. Now today's newspaper article in the Hindu, and also the IPCC and television channels have constantly said, this is going to be the new norm. We will have periods of very intense precipitations, sort of squeezed in a matter of days, and then we have lean periods with no precipitation at all. So that's quite worrying. So with that account, I think all of us would like to know if we were to engineer and change patterns of rainfall artificially, we should first know how droplets group together to form rain. That is actually what I have been working on for a long time. So a little bit about the processes. Here you can see a cloud. It has a cloud top. As I showed, it's quite cold. The bottom is warm. At the initial stages, rain formation happens by a process of collision coalescence. Here you can see small droplets and larger droplets. The larger droplet falls much faster, and as it falls, it captures smaller droplets. So this is collision coalescence. But for the larger droplets to form, there is a threshold amount of liquid water the cloud must have so that small droplets of a similar size can actually self-collect. So self-collection produces a few large droplets, and once a few large droplets form, you have quite fast rain formation. In technical parlance, these are called autoconversion and accretion, and the English gives away the sense of the physics. Accretion is sort of material depositing on layers. This is self-collection and autoconversion. So this is just to show that we are talking of scales, tiny aerosol particles, then cloud droplets, then all the indentations in the eddies. So they vary over 1,000,000 times. Imagine with this variability in the scales of the operating procedure, to cover this variability on the entire planet, we would need billions of grids. That's why we need supercomputers. I have to tell a little story. When I was growing up, during the Bangladesh War, America was very cross with the Indian government. And to punish India, they said, we are going to stop the transfer of supercomputer technology, knowing very well that millions of Indians depend on an accurate forecast of monsoons so that the poor farmers can plan better. So supercomputers have to be used to predict the onset of precipitation during the monsoons and save millions. This was stopped. And Indira Gandhi, being Indira Gandhi, she called up Professor P.K. Das, who was the Director General of Meteorology then, and said, ensure that we are able to develop our own supercomputers. India did that quite rapidly and quickly. We are not reliant on American supercomputers. In a private university like VIT, we have several supercomputers where we run these, and because of that, India is on the forefront of weather forecasting and geoengineering experimentations. So we have a variety of models from the microscale to larger Ds, and a lot of my own project students, Siddharth and Prahlad and Vishnu, all of them run them on supercomputers. It's a little bit of digression. This is the formation of this life-giving clouds with its drama of lightnings and thunder. And I have highlighted a line, a surge and hiss and onset of huge rain. I'm very, very surprised Sri Aurobindo used that crucial word. So onset, I'm going to talk about that later, but let me read parts of it. How he describes the advent of monsoon. Armies of revolution crossed the time field. The clouds' unending march besieged the world. Tempest pronunciamentos claimed the sky, and thunder drums announced the embattled gods. A traveler from unquiet neighboring seas, the dense-maned monsoon rode neighing through Earth's hours. So you saw in the BBC video that moisture is picked up largely from the Indian Ocean, and he's kind of likening it to a god riding on a horse, a traveler from unquiet neighboring seas. And what are the neighboring seas? The Indian Oceans. The southwest monsoon is riding through the moisture-laden air of the neighboring seas. And now look at the use of words. Thick now the emissary javelins. He's used the word javelins because, you know, this process of autoconversion and accretion produces very large droplets that's almost coming out of the cloud base like a bullet, almost like a javelin you shoot. It's coming with tremendous velocity, and enormous lightning split the horizon's rim, as you see, and hurled from the quarters as contending cats married heaven's edges steep and bare and black. A surge and hiss and onset of huge rain. The long, straight sleet drift, again, mark the words. The upper reaches of the clouds are frozen. We have frozen hydrometeors consisting of sleet, and bottom we have warm rain. The long, straight sleet drift clamors of wings storm-charged, throngs of wind faces rushing of wind feet, hurrying swept through the prone afflicted plains. I showed you examples of a parched afflicted plain. Heaven's waters trailed and dribbled through the drowned land. Again, the use of adjectives. Waters trail behind one another. We have one patch and then another patch of rain, and a dribbling is associated with drizzling. Then all was a swift stride, a sibilant race. That adjective is referring to the noise associated with the falling rain. Or all was tempest shout and waters fall. So I'm going to play another video now.
If you've ever looked at the weather forecast, you might be familiar with a percentage. It's the probability of precipitation. For example, 60% rain means that when similar forecasts have occurred in the past, only 60% actually rained. Uncertainties can sometimes leave us unprepared for storms and floods, but predictions improve as we monitor storms in greater detail. And now, NASA's newest precipitation satellite, GPM, is measuring the individual water drops that make up a storm.
GPM is the first time we've been able to get this type of information on a global scale.
To understand why this matters, it helps to know how weather predictions are made. First, computer programs known as weather models turn the processes in the atmosphere into math equations, governed by the laws of physics. These equations receive measurements of the land, sea and air to get a view of the atmosphere's current state, then predicts how it will change over time. To ensure predictions are correct, equations need to represent the atmosphere accurately. But one thing that's uncertain in the equations is how precipitation is structured within storms. A storm is made up of water drops of different sizes, but without knowing these measurements, many weather models operate under an assumption.
What they do instead is have some assumption about how that's distributed. So as an example, for every 100 small drops, there would be 10 medium-sized drops or just one large drop.
Assumptions are made because researchers have only studied drops in isolated areas. Now, for the first time, GPM is measuring the size and distribution of drops around the world. If we go into a storm, we'll see varying drop sizes labeled different colors. Near the top, there are many small drops around 0.5, 1 and 2 millimeters. As they fall to the middle of the storm, some drops bump into others, causing them to grow in size. Right at the bottom, drops can grow around 4, 5 and 6 millimeters. This 3D mosaic of water drops is called drop size distribution. It shows a high concentration of small drops coloured in blues and greens near the top, and lower concentrations of big drops coloured in reds and yellows near the bottom. A storm with a higher ratio of red and yellow will contain more water than a higher ratio of blue and green.
Without knowing the relationship or ratio of those large drops to the smaller and medium-sized drops, we can have a big error in how much rain we know fell, and that can have some big implications for knowing long-term accumulations, which can help for flash flood prediction.
Not only does it give a more accurate measurement of rainfall, but drop sizes also give insight into the winds within a storm.
Thunderstorms have a lot of wind associated with them, and we all know this, but the strength of that wind actually depends on the size of the drops that are falling from that storm in some ways. Because a storm with small drops will have more evaporation, which cools the air more, which creates stronger winds. We've never been able to see how water droplet sizes vary globally until now.
So what causes them to vary in different places? One factor is the temperature of the environment drops grow in.
In the mid-latitude, a lot of those raindrops actually originated as snowflakes or even hailstones, and snowflakes can grow a lot larger than cloud droplets can, so you have these big snowflakes that then melt into big raindrops. In contrast, over the oceans and in the tropics, they tend to be smaller, and the reason is because smaller raindrops tend to originate from clouds that don't have any ice in them.
It's worth noting, however, these measurements are only a small part of the equation.
The drop size distribution is one of many factors that determines how big a storm will grow, how long it will last, and how much rain it will ultimately produce.
As GPM improves our understanding of precipitation from space, that information will be vital in improving weather models and thus helping us better predict and prepare for our weather.
So with that background, we'll be in a position to sum up our own research that we conducted in VIT using these supercomputers. So this was done by Siddharth Kumar, who's sitting next to me. So here you can see the actual, a picture from the India Meteorological Department that is showing a lot of rain bands in southern India. This is a December simulation northeast monsoon. We are trying to replicate the Chennai deluge. And so we solved all those equations through this code, and this is what we modeled. And we wanted to compare the likeness of the modeled patterns of rain distribution with the observations. You can see a tremendous likeness. All the large features as well as the nuances of the smaller features were quite accurately captured. So now we come to the problem of excessive flooding, of inundation over some of the city's most vulnerable parts. Earlier on, I had said that every time there's a failed monsoon, the wealthy farmers are not affected, but the poor farmers who own small croplands, they are severely affected. Now let us see it with how affluent people who live in high-rise towers, they wouldn't be affected by overground flooding, but the North Chennai slums, we particularly did a project on 5 slums in Chennai, Ilangu Nagar and Perambur, and these are some of the slums. And what you see here in lines in blue are the natural flow lines that have largely remained undisturbed ever since Chennai city was built. And the black areas are highly populated areas. So the slums in North Chennai are quite populated. And the red dots are the North Chennai slums. And we are the greens are the small local tributaries. And here we are showing vulnerable watershed areas that include a lot of shanty towns. They live in kacha houses. So if you remember, Sri Aurobindo had used the word the onset of rain. And even in the BBC video, that phrase was used. This is quite a recent thing so Siddharth and I, we want to develop mathematical formula that do not require a supercomputer to tell us the onset time. You could get an alert on your mobile phone by solving a quick MATLAB code that'll come onto the slum dwellers' mobile phone, and they would be told 3 days in advance, look, after 3 days, your lived-in area is going to be inundated, so better move out. So in that process, we are giving it a sufficient lead time to the city planners. And then delineating drainage patterns and the spill regions where the water will flow into. So can I show them the paper? I'll just click on it. Yes. So this paper was published quite recently, and I will share it with the people who are registered for free. And we are saying quick predictions of onset times and rain amounts from monsoon showers over urban built environments. I won't go into the paper, but I'll roughly show you what was done. So this is what Dhruv did. He was ferrying standard people for that deluge through boats. And this is the precipitation event that we studied. And so then what we do is we find out what the actual satellite observations are showing, and then we are comparing. So we have to know what the temperature, pressure of the cloud base, all of that. And now rain, you must understand, rain doesn't come out of nowhere. You first must have clouds. So the cloud water gets converted to rainwater beyond a threshold. So when you have a decrease in cloud water, you have a concomitant increase in rainwater. So the E-folding time tells you at what time. When cloud water has depleted by a certain amount, 1 by E of its original value, then that is a reasonable estimate for the onset time of rain. So what Siddharth derived was, he derived formulas and he was comparing them that his simple predictions, how do they match with the full supercomputer run model? And I'll just go to the end result. So what we found was they actually are quite accurate. So it is quite possible to give phone alerts using a non-supercomputer generated, and this was done for the first time. It's part of his PhD, and this has been recently published. So with that prediction, we know how much water will drain a certain part of the city, which is crucial information to save millions of people from a lot of misery. Now let's, what's happening? Yes. Now let's again see, we saw that we receive a very small amount of received fresh water from the clouds. What did the ancients do? I'm very proud to say that I now live and work in this highly educated and developed state of Tamil Nadu. So the ancient Tamils 2000 years ago, they knew how to collect received precipitation from the monsoons, store it, and engineer its release over across to the Kaveri Delta, so that Tamil Nadu is indeed a rice bowl of India. So this is one of the oldest dams in the world, and the Chancellor of VIT had called me that, Ghosh, can you start student projects to look on the iconic dam that ancient Tamil Nadu? I said, yes, of course, I'd love to do that. So, but Tamil Nadu also had a system of eries which collected rainwater locally, not such massive engineering structures. So in the late 1st century AD, the Kalanai Dam over across the Kaveri Delta was commissioned, and early 2nd century AD, it was completed. And then in 1839, Sir Arthur Cotton, so he reinforced it, and people love Arthur Cotton. There's a statue. So he reinforced it without disturbing the ancient structure. And the dam stones in 1836, the dam stones were 86, they removed, and the falling shutters were installed. 1922, sort of some more fine alignments were done. So we went on site and did an on-site survey. I'll come to that. A glance at history, the world's oldest dams. So you had the oldest one in 1304 BC in Syria, and then you had a contemporary of the Kalanai in Spain, and another two in Spain, and the Kalanai Dam Grand Anicut, 2nd century AD. So we should be very proud of what they did. So the prime function was to retain the supply in Kaveri and its branches and pass on the surplus into another small river called the Kolarun. And you can see the eddies forming. And it is on record that thousands of slave laborers brought from Ceylon. Yesterday we studied Anuradhapura, and there was a deep connection. So Rajaraja Chola's territory extended beyond Tamil Nadu and spilled over into Sri Lanka. So laborers were brought in from Sri Lanka to do the work. So this is an image of the modern Kalanai Dam, and then the spilling over of the water in a controlled manner in the adjoining plains. So the blue line are the trade routes, and the Chola territory, the extent of the Chola territory in blue, and the Chola influence, indirect influence on the right. And so this has been this is another example. I mean, I'm calling it consciousness of the built environment. Built environments do not refer just to our lived in houses and cities. The built environment also includes grand structures. So this is a grand hydraulic structure that has stood strong for 2,000 years. And it was initially constructed from unhewn stones. Like in yesterday, we studied the Delphi amphitheater in ancient Greece. There they used locally quarried stone. They didn't import the stones from here. Again, here, this was used with unhewn, locally sourced material. Like in Anuradhapura had shown an edict, an Ashokan edict. So this is another ancient edict inscribed in Tamil. So that's the exact Tamil. I won't read it out, but the translation is on the right. And the translation that lives on raindrops singing its praises, the Kaveri that springs from the mountain and floods down to the surging sea, will never fail, though clouds may fail. So he is so sure of his royalty that he has created an engineered structure that farming will not stop, even though the clouds may fail. And this is an example of the unhewn stones that were used to build this dam. This is a Google map image, and this is the Kaveri River, and that's the exact point where the dam was built. Now, I will go into the basics of this built environment. What is the purpose of a dam? It is an engineering intervention to hold intense receipt precipitation on one side so that it doesn't unleash its fury downwards to inundate and flood. So the whole purpose is to check the flow of water from one side to the other through sluice gates and various other mechanisms. So this is a picture of Sir Arthur Cotton, and in a typical Tamil fashion, a temple was built to venerate this person. And the current dam dimensions are given here. And so some part of our research, we had to look at the pier thickness and the shutter height and all of that over the Kaveri River and also the adjoining Vennar River. And we have, is this? Yes. So we have written a book, you can, so which is now stored at the Smithsonian Library as one of their resources. But unfortunately, it's now sold out. I'll let the people know when this will be available again. This is my book with Manu, and this has been translated into some European languages. It's an interesting read. So now what is shown in the book? The main challenge was the Chancellor asked us, you have to find out why was it able to survive 2,000 years in its history without getting massively degraded. There were some enhancements made, but more or less so we had to create a model and had to examine the stresses that the structure's most vulnerable points experienced. So this was again done with millions of grids, and a simulation was done. What is shown here on the left is the turbulent kinetic energy. And these are contours of turbulent kinetic energy of the water that is touching the structure. I'll draw your attention to the streak of red. That is the region where you have the most intense TKE. That intense region is actually not making physical contact with the structure. It is above it. Perhaps that was a saving grace. Had it touched, perhaps the dam would have collapsed. I'm going to show you a little simulation. As I was saying, that water that is separated by the dam is not allowed to gush through dangerous velocities. I'll run the simulation. So the greens are the low velocity waters and the reds are the high velocity water. I'll play that again. You can see that as it flows through the dam, it's almost entirely green. And we gave the velocity of the waters from the supercomputer simulations and the amount of rainwater, from the intensity of rainwater and the collection. So to summarize, the built environment has been played around with royal support, building grand structures, building cities to manage cultivation that shaped Tamil civilization. Now I shall come to how do we cope with monsoon fury. So again, from the book of Eternal Night, a world in a dumb eddy of meeting winds. I'm not sure, Bilton and Krishna Siddharth, are you there? Are you listening?
Hello, sir. I'm here.
Hi, Bilton. Hi, Bilton. And Krishna Siddharth. Yes. So Bilton is now an aerospace engineer at Airbus in France, and he's speaking from France. And Krishna Siddharth will soon go to Norway. So what we have done in this paper is Cyclone Hudhud affected our country quite severely. We first simulated the cyclone, and their project was to look at how the roof design, again, an example of the built environment, how the roof design copes with an onslaught of hurricane. So before I go further, during the time of the British Raj, there were standard guidelines by the building code, and they suggested a pitch angle of 11 degrees. So again, with computational fluid dynamics, we replicated the impinging of hudud on different roof shapes. So we have a dome shape and then a quarter circle. Then we have a flat roof. Mind you, the shanty towns in Chennai all have flat roofs, and a steep gable roof and a shallow gable roof. And then we also looked at the turbulent kinetic energy, because that's the singular parameter that can destroy a house at the velocity of the wind. So to, let's see, again, the registrants of this course can have full access to this peer-reviewed journal publication, an example of a consciousness of the built environment, countering tropical cyclonic storm impacts on low-rise houses. So I won't go into this. So what we found was the Indian guidelines that were issued 150 years ago needs to be modified. We have suggested a better pitch angle, which is not far removed from. So Bilton, would you like to just bring in some aerodynamics that you're doing in France? Can you bring in a bit, in a sentence or two, about this study and how it relates to what you're doing now?
Thank you very much, sir. So basically what we tried to do in this study is take in common recommendations by the Indian guidelines and to try to analyze all the recommendations and some novel designs that we proposed as well that could possibly have better aerodynamics to reduce the stresses over the houses. So on performing these simulations, the main focus was on the pressure and the turbulent kinetic energy that is acting on these structures. And based on how the roofs are contoured, the flow is different for the different roof shapes that we have studied over here. And the best case that we found from the simulations was the shallow gabled roof. And one comment that I wanted to add regarding the turbulent kinetic energy is that in many cases, you see that they do not actually make a physical contact with the structures. And that is because the turbulent kinetic energy is related to the fluctuating part, that is the turbulent part. And when the fluid makes contact.
That's too much. Yes, fine. So that was very, very nice. So again, just as in the Kalalaidam, the turbulent kinetic energy, for a good structure, the highest levels of TK should not make contact with the structure. And are suggested. So are we suggesting a shallower gable or a steeper gable built?
It's a shallow gable roof, sir.
Yes.
Because the flow of the velocity.
Yes. Krishna Siddharth, you work at an IT company. Do you think that Indian IT companies are kind of customizing research to meet societal ends such as this? A brief comment on this.
At the moment, there seems to be no.
I don't think he can hear this. Anyway, so we've seen.
So I think he started speaking.
Yes, so he can speak. Yes, Krishna, so very briefly, what directions are the IT companies in India so that disasters do not happen?
At the moment, when I look at the IT industry structures, they are not, they don't deal too much with the aerodynamics and how to counter cyclonic windstorms at all, but they are more focused towards energy conservation.
All right, focus. Thank you. So we've seen that, again, a bit of a summary. Received precipitation is minuscule. It has to be conserved. It was conserved very well in the past. And our civilization bordered on collecting as much of rainfall and letting it out in a very controlled fashion so that paddy cultivation is possible in a controlled manner. So this calls for a SAARC cooperation. Now we come back to how monsoons shape civilizations much early on. Paleo channels have been discovered at the Thar Desert, and which is a tributary of the legendary Saraswati, and those are the dates. And here you can see the regions. Much of it is in Pakistan, but some of it is in India. So Michael Danino has written a very authoritative book. He's called it The Lost River. And the economist Sanjeev Sanyal, he gave a very nice talk at the Hall of Harmony in Pondicherry, where I attended, on his book on these aspects. So let's quote Michael Danino. He's saying, on the trail of the Saraswati, the Vedas of old spoke highly of the mighty river, and 3 hymns were dedicated to her. The waters are lauded as a great flood. She is great among the great, and he uses phrases, the Vedas use the phrase limitless and swift, and she's the mother of all waters. So that's the region. So this is an image of Suktako, a Harappan coastal settlement in Pakistan. Now I'll come to the nitty-gritty of the building forms. It's mainly desert area. And you can see isolated flat-roofed houses. And one of the reasons attributed to the disappearance of the Indus civilization is the monsoons had failed and the Saraswati had dried. And because of the lack of water, the residents moved away from the region. So we did a project as part of the research embedded project for mechanical engineering students. And I shall show some. So this is an image of, what ancient cities look like. I would like to draw attention to the fact that they used baked bricks. They were not fired bricks. Baked bricks are more sustainable than fired bricks. They have a lower carbon footprint. And the Aurobindo Earth Institute pioneers this. And the Earth Prize given by Richard Attenborough and funded by Prince Charles, the last Earth Prize actually went to an Aurovillian. We are very proud of that. They invented the concept of city-scale drainage and clustering of houses along a street. This was first developed in the Indus Valley civilization. Again, through computer modeling, we completely recreated a fortified Indus city. And so we knew that there were at the most 2-storied, and what we have said here, that we used dried mud bricks, as I said, and the street widths were developed, and shared walls. Now, if you have a shared wall, this is conserving resource. So one material for one wall is not used. So we completely recreated these Indus Valley houses. And we found that the shared walls aid the setting up of convective currents. Yesterday, we looked at ventilation. We looked at mixed ventilation, displacement ventilation, and we agreed that if there are two apertures, as here, then there's displacement ventilation, which is faster ventilating air and more air changes per hour. Mind you, during COVID, the guidelines was that you should have frequent air changes per hour in your room. And I was making inquiries at the CMC. Dr. Gagandip Kang is the first woman president of the Royal Society. I mean, even for an elite institution like the CMC, in the most hospitals anywhere, the air changes per hour is about 4 or 5, and ideally it should be about 20. It's very expensive. So during COVID, expensive airlines used HEPA filters on its windows to not just filter out the sneeze droplets, but they ensured there were frequent air changes per hour. So there were frequent air changes per hour mediated through displacement ventilation in the Indus Valley houses. Now we're coming towards the end of this lecture. These are pictures of Auroville, which got the last year's Earth Prize. So on the left, I'm showing a bamboo grove in front of the Asana guest house, which Nirodha inaugurated. And then in the interior, you have a lotus pool. So and you have open plan building, again, displacement ventilation, and these lotus pools add an aesthetic dimension quite significantly. And just like in ancient Anuradhapura, it is promoting hydraulic air conditioning, and it does not require artificial air conditioners. This is the Savitri Bhavan, again, built in Auroville, the building has very large glazing ratios. It has studios and galleries. It lets in natural light, and you don't need artificial lighting. And this is an interior of an hostel in Savitri. I stayed in that hostel, and again, they have used a pool of water body. This is in the dining area, completely open plan, and the rooms do not have air conditioning. Alexander, are you there by any chance? Alexander from Savitri Bhavan. So he lives here, but I will tell. So what was interesting is each room opened onto a courtyard, and there was wire meshing that let in outside air, and the walls of the room did not cover the floor to the ceiling. There was an aperture at the top that went into the bathroom with a wire meshing, and the bathroom opened out to this corridor. Can you see the vent here? So the continuous cross current, and when the wind blew over this water body, it was promoting hydraulic air conditioning. So I'll play a little bit of the mother's voice.
Autumn led in the glory of her moon, and dreamed in the splendor of her lotus pool.
So autumn led in the glory of her moons and dreamed in the splendor of her lotus. That's splendid not just because they lend an aesthetic dimension, they're splendid because they're conserving crucial energy and reducing the carbon footprint. So another example of large-scale built environment, this is the 1,000-pillared corridor in Tamil Nadu. And we shall see how Sri Aurobindo describes such grandeur. Her heaven-carven chariot with its fretted wheels threaded through clamorous marts and sentinel towers, past figured gates and high dream sculptured fronts, and gardens hung in the sapphire of the skies. Pillared assembly halls with armored guards, small fanes where one calm image watched man's life, and temples hewn as if by exiled gods to imitate their lost eternity, often from gilded dusk to argent dawn, where jewel lamps flickered on frescoed walls. So this is the most striking example where monsoon rain was used to enhance the quality of art. So this is the famous Arjuna's penance in Mamallapuram. And we do not know the artist. It's over 2000 years old. And yesterday, Dhruv had asked, in the scheme of things, do animals come in? They certainly did in the past, from where you come from, Dhruv. You can see elephants, then you can see monkeys, and you can see celestials. And then there is a natural cleft, a gully. And I have perused literature that suggested this outstanding frieze enlivens up to its most glamorous best when there is a huge monsoon shower that is pouring rain through that gully. And if you view this panel when it's raining with the gushing rain through that gully, it's an altogether different experience. It's much more alive than viewing it when it is dry. So I call it the universal voice of meteorology and artist's take. Now, you must not believe that the monsoons happen only in India and South Asia. The African continent also receives monsoon, and at Leeds University, we had a project called AMA. So it's called the African Monsoon Experiment. And Dhruv and Siddharth and I, we went to the Masai Mara National Park to see how the housing there coped with the vagaries of the climate. So we have published a book again, but this is not sold out, it's still available. This is a house, again, you see a flat roof with sustainable features. It is using dried up grass, and it has a baked wall, practically zero carbon footprint, creating that house. And this is so yesterday we discussed the advantages of having wall layering. So modern houses in Britain, they have different layers of insulation, foam and fiberglass, and so that there's a retarding. In Britain, they want the warmth to be retained. And in India, we want the reverse, the cool to be retained. So these houses, they have layering. So have a layering of cow dung and clay soil, grass and wood, and then air gaps. We saw that in Aratipura, how the air gaps made the Jain dormitories quite sustainable. So they have all of that. And we looked at the temperature profile inside. It was quite comfortable inside. And Siddharth currently is at the India Art Fair with a lot of artists, and he's an outstanding photographer. So I'll use some of his prize winning. He was named the European Photographer of the Year. The stark contrast between the darkened indoors of a Maasai household in comparison to the brightly lit Mara outside. This is outside, and that reflects on this child playful countenance. And I began my lecture yesterday that literature and poetry is a study of contrasts. And here you see the same study of contrasts in a beautiful photograph. So again, some poetry in witnesses' occult rooms with mind-built walls, on hidden interiors, lurking passages, open the windows of the inner sight. He gazed across the empty stillnesses and heard the footsteps of undreamed ideas in the far avenues of the beyond. So the slight slant of this little Masai Mara boy holding onto something as if he is hearing the footsteps of undreamed ideas, and he's gazing across the empty stillnesses, and you have a bunch of firewood in his built environment, his own world. A little bit about indices of thermal comfort. We discussed a lot of that. How much more? It's nearly time. I'll wrap up. I'll just go over to one slide. So here on the y-axis, we have the temperature, and here the time of the day. So the red line is the swings in temperature, the outside temperature. So during midday, you have temperature rising to the high 30s, and at night it's dipping down to a low 15. And you have this repetitively every day, day in and day out. And a building is supposed to be a climate moderator. You say that it's a good building if it is able to manage the rapid swings into something more mellow. Instead of this very large amplitude swing, if the temperature distribution is mellowed down into a more manageable wave structure, then you would say that the building has performed better. And the damping ratio, the larger the damping ratio, the more efficient is the building. So people experiment with various types of building, they orient it in different directions, use layering in the walls to achieve. So our grandfather's house, and the grandfather, Moitre's and mine, so it had very high ceilings and very, very thick walls. And indoors were quite cool because it was managing this modulation quite effectively. So then to wind up, I've called this course The Consciousness of the Building Environment, and sages and poets and artists, they seem to be conscious of this fact. So Sri Aurobindo writes in his Letters of Yoga, there is a consciousness in each physical thing with which one can communicate. Everything has an individuality of a certain kind. Houses, cars, furniture, the ancient peoples knew that, and so they saw a spirit or genius in every physical thing. So I'm going to play a video from my beloved Pondicherry, which worked with these ideas.
Golconda, located in Pondicherry on the southeast coast of India, was designed by Antonin Raymond and George Nakashima in 1935 as a multi-story dormitory of Sri Aurobindo's ashram. This building has a world stature, both architecturally and in its bioclimatic response to a tropical, warm and humid climate. It has the reputation of being a well-maintained, comfortable building, although it has no mechanical cooling system. While gaining from the practical experience acquired in the vernacular buildings of Pondicherry, the architects have tried to translate them into materials that are offered by the modern world. The local climatic conditions were taken into consideration, and the building was given the most logical shape dictated by the local conditions. It is an exposed, reinforced concrete frame structure with traditional lime plaster on the brick walls. The fundamental principles of architecture, simplicity, economy, beauty, and closeness to nature, were consciously and consistently observed. Golconda is truly timeless in its essence and a masterpiece of architecture. The roof is made of large and thin precast curved cement concrete elements, creating a ventilated airspace over the third floor concrete slab. The ends of these precast curved elements on the north and south are sealed with perforated concrete slabs. The double roof was important because of the almost continual intense heat of the tropics. The convection of air keeps the top floor rooms almost as cool as the ones below. Both north and south facades are fully openable with louvers, which can be fully opened, half opened, or closed by a series of simple state-of-the-art brass bars with notches to adjust the angles. Interestingly, all along the north facade, there is first the corridor which connects all the rooms. The decision to keep the corridor in the north side is an important one, since Golconda is situated on 12° north latitude with summer sun penetrating on the north. This is how the rooms are kept cool all the year round, even in the hot weather. The louvers are easy to operate individually and allow for personal preferences. Rooms are separated from corridor by wooden sliding doors that allow air to circulate freely when open. The walls of the rooms are of brickwork covered with seashell lime plaster. There is no need to paint these walls, and they retain their hygroscopic quality even after 85 years. The landscape gardens on the south and north have a sense of wideness due to the angle given to the building. Enclosed on all sides by high walls, they become peaceful cloisters where one can walk and relax. The simple landscaping of the surrounding garden, with its trees and grass and shallow pools, carries out the effect of coolness that is realized structurally in the building itself. The high protecting wall holds in the air that is cooled by the attractively landscaped garden and keeps out the heat of the surrounding heat islands of unshaded streets. To further the cooling current of air in summer, as often there is no movement of air at all, the garden on the northern side of the building was left rather bare, whereas the garden space available in the southern side was planted with many trees and shrubs. By these means, the rooms at Golconda are always cool and did not require any mechanical ventilation. The rooms are provided with a ceiling lamp for general lighting and a desktop lamp for task lighting. They were initially not even equipped with ceiling or table fans for ventilation, but over the years, construction activities around the town and hard surfaces have contributed to urban heat island effects. As a result, some rooms are provided with table fans used for personal cooling only when it is really necessary. In articulating an unambiguous stance towards minimal resource consumption and bioclimatic architecture, the building champions a unique aesthetic. The story of Golconda Dormitory, in both design and construction, remains quintessentially international. Having outlived its designers, it celebrates their ideals of a progressive vernacular modernism, simultaneously resonant in the local and global context.
So while Mira Alfassa, the mother, mentioned such an outstanding India's first energy efficient building in Pondicherry, something similar was going on in Tagore's University, Shantiniketan. So the mother and Rabindranath Tagore were very good friends. So at one point of time, Tagore asked Mira, will you take over Shantiniketan? She said, no, I have other things to do. And he was very conscious. Tagore was very conscious. This is Mother with Tagore and her husband in Japan, in Kyoto. Tagore also created climate-sensitive buildings, and the Bengal School of Art embellished it with outstanding works of art to unleash a certain form of modernism that was done for the very first time. So now you can see paintings and alpona on these buildings of new forms of art draped onto facades. This is happening now all over the world. And he had such tremendous fondness for some of these buildings that he would move from one building to another. And there's one particular building called the Shamoli, which he really liked. And I shall play a little bit. Is this the first one? Yes. I shall play a little bit of music just for a few seconds, just to show that a single person created poetry, set it to rhythm and music so that it evoked the drama of the monsoons. So here's an example. Now an example of how poetry composed by him in a richly cadenced voice of the son of Qazi Nazrul Islam. Again for 30 seconds.
Ogo sonnasi ki gan khanalo mone guru 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 nachero damoru bajilo khane khane tomaro lolate jotilo jotaro bhar নেমে নেমে আজি পড়িছে বারংবার বাদলো আধার মাতালো তোমার হিয়া বাঁকা বিদ্যুৎ চোখে ওঠে চমকিয়া চিরজনমের শ্যামলী তোমারও প্রিয়া আজি এ বিরহ দীপন দীপিকা পাঠালো তোমারে কোন লিপিকা লিখিল নিখিল আখির কাজল দিয়া চিরজনমের শ্যামলী তোমার প্রিয়া
Shamoli is, of course, a built environment. It is a building that Tagore loved, and he uses the building in one of his poems. So I shall end with another 30-second unaccompanied voice sung by Vishnu to evoke the monsoon.
भरन लगी भरन लागी बूंदरिया भीगी जाऊं मैं पिया बचा ले जाऊं मैं पिया बचा ले लियो भीगी जाऊं मैं पिया